Let's start with Module 3 of KTU Honors Number Theory. First topic is arithmetic of ZP. So any linear congruence AX congruent to P mod n is said to have a unique solution mod n if the GCD of A and n is 1. If n is a prime number P, then the GCD of AP should either be 1 or the number itself. The GCD of a prime number and another number is 1 or the number P. If it is 1, which means it has a unique solution mod P, and if it is P, P divides P, every x is a solution or no x is a solution. The polynomial AX minus P has a degree D if 1 over ZP. And we know that any polynomial of degree D has at most D distinct roots or solutions. Next is Lagrange's theorem. Lagrange's theorem states that if P is a prime number and if f of x is any function, is a polynomial with integer coefficients, then the congruence of f of x is said to be congruent to 0 mod P if it is satisfied by at most D congruence classes. So we consider the polynomial f of x is equal to x square plus 1 and to find the roots of ZP. So here we take all primes less than 17, that is 2, 3, 5, 7, 11, 13 and 17. So when P equal to 2, there is this one class 1 which is equal to Z2. So in order to obtain f of x is congruent to 0 mod P. So here f of x congruent to 0 mod 2. What value of x can be given? So here there is just one value of x, where 1 square plus 1, 2, and f of x is 2, then 2 is congruent to 0 mod 2. And thus there is just one class 1 in Z2. Next, for the prime number 3, if you give 3 square, you get 4 plus 1, 5. And 5 is not satisfying this condition, 0 mod P. So it is not present. So there are no classes in Z3. Next, if we take the prime number 5, we get 5 square, 25 plus 1. That is, if we get, in order to get the prime number 5, if you take the number 2, you get 2 square plus 1. That is 5. So here, if you take 2 or negative 2, whatever it is, you will get 5, f of x congruent to 0 mod 5. So there are two classes, plus or minus 2 in Z5. Next is, for P equal to 7, is this possible? If we take 3, do we get it? No. So next is, so there are no class. For P equal to 11, can we obtain 11 in any way? If we take 3, 3 square, 9, 9 plus 1, 10. No, it's not possible. Next we need 13. So for 13 we try with 4 square, is it possible? 4 square is 16 plus 1, 17. No. Next when we take 5, we get 25. 25 plus 1, 26. So yes, 26 is congruent to 0 mod 13. Since 13 to 2 is 26. So again we can say there are two classes, plus and minus of 5. And then we take 17. We'll check whether we can obtain 17 or not. So if we take 4, 4 square 16. 16 plus 1 is 17. So yes, 17. It is congruent to 0 mod 17. So you again have two classes, plus or minus 4 in Z17. And thus the question is to find the roots in ZP. So in Z2, for P equal to 2, we have one class. Then for Z is equal to 3, there are no classes. And for Z is equal to 5, we have two classes. Z is equal to 13, we have two classes. And for Z17, we have another two classes. Next question is, to find all the roots of the congruence, f of x is equal to x raised to 17 plus 6 into x raised to 14 plus 2 into x raised to 5 plus 1, that is congruent to 0 mod 5. So here the prime number given is 5. So we have to find it in Z5. So here we replace x raised to 5 with x. So we can write x raised to 17 can be written as x raised to 5 the whole cube into 2. That is x raised to 5 to 3 15 plus 2 is 17, right? So x raised to 5 the whole cube. So x raised to 5 is x. So x raised to 3 into x square. This is again x raised to 5, which is replaced with x. So this x plus here x raised to 5, this x raised to 5 plus this x raised to 17 became x. So it became 3x here, 3x plus 1, and x raised to 14. Here x raised to 14, which can be replaced with x square. Now we have simplified this. Congruences with a prime power modulus. We have seen before that it is easy to find a solution x1 for linear congruences that are of the form ax congruent to b mod p. But if you have any prime number p where the GCD of a and p is 1, now we'll illustrate that we can find a solution x2 for any ax congruent to b mod p square such that x1 is equal x2 is equal to x1 mod p. x2 is called the lift of the solution x1. Similarly, we find another solution x3 such that ax congruent to b mod pq. Now we are going to take the power of prime numbers. So where ax congruent to b mod p, GCD of a and p is 1. Next we find ax congruent to b mod p square, b mod pq, and such that the lift of x2 and hence x1 as well as x3, that is x3 now became, we can say that x2 congruent to x1 mod p. So x3 is congruent to x2 mod p square now. So any solution modulo higher pass, that solution of the higher pass is called a lift of the solution of lower pass. That is here x3, it is a lift of x2 and hence of x1 as well. So if you take the example of p equal to 7, consider the linear congruence. Then we have 3x congruent to 5 mod 7 cube. We wrote that 3x is congruent to 5 mod 7 cube. So when we look, 5 is the inverse of 3 modulo 7. So we have a unique solution x1 is equal to 4. So we can write 3x minus 5 congruent to 0 mod 7. We lift x1 to as a solution of x2. So we got 3x minus 5 congruent to 0 mod 7 square. And x2 to the solution of x3. So we get x2 is equal to x1 plus 7a1, which is equal to 4 plus 7a1. Then we have found x2, 3 times x2 minus 5 is equal to 0 mod 7 square. We simplify, you get 7 plus 3 into 7 into a1 is congruent to 0 mod 7 square, which then you take 7 out, cancel 7, you take the 7 out from here, cancel the 7 to get 1 plus 3 into a1 is 0 mod 7, which is again now we have to check whether what value of a1 would satisfy this condition. 1 plus 3 dot a1 is equal to 0 mod 7. So if you give a1 is equal to 2, we get 3 into 2, 6 plus 1, 7 is congruent to 0 mod 7. So a1 is congruent to 2 mod 7, that is a1 is equal to 2. Then we substitute it in, here, x2 is equal to x1 plus 7a1, x1 is equal to, that is 4 plus 7 into 2, that is equal to 7 2 is 14 plus 4, 18. So next solution for congruence modulo 7 square is 18. Next we have to raise it to the, lift it to that of x3. x3 equal to x2 plus 7 square a2. So first, so here x2 was x1 plus 7a1 and x3 becomes x2 plus 7 square a2. So now we substitute it here in 3 into x minus 5 congruent to 0 mod 7 cube. So we get 3 into 18 plus 7 square a2 minus 5 congruent to 0 mod 7 cube. Expanding 49 plus 3 into 7 square a2 0 mod 7 cube. Now what value of a2 would satisfy this condition of 7 cube? Here 49 can be written as 7 square. So we take 7 square common from both to get 1 plus 3a2 congruent to 0 mod 7. And now what value of a2 would satisfy this? So when you give a2 equal to 2, this is condition satisfied. So we can write a2 congruent to 2 mod 7. And thus again we get solution as 2. So we substituted there 18 plus 7 square a2, which is equal to 116, which is a solution of given congruence, and it is a lift of x1 is 4, the congruence modulo 7. Next is nonlinear congruences modulo prime powers. Now we will do the above illustration for a nonlinear congruence. We will take a nonlinear polynomial f of x with an integral coefficients and then show that we can lift one solution modulo p to another solution of some power e, where we cannot do so for another solution modulo p. So here we are considering a cubic polynomial f of x cube plus 3x square minus 2x plus 5. So we are considering a prime p, so f of x. We are considering a linear congruence f of x congruent to 0 mod 7 cube. We need to solve. So one can directly check that 1 and 2 are the only roots of f of x modulo 7. So here f of x congruent to 0 mod 7 cube. First, we try to write in the form f of x congruent to 0 mod 7. So for this to be true, f of x, when given the value of 1, we get 1 plus 3, 4, 4 minus 2, 2, 2 plus 5, 7. So 1 is a solution for f of x mod 7. And then when we give 2, again 2 cube 8, 8 plus 4 3s are 12 plus 8 20 minus 4, which is 15 plus 15 20, 1, which is again a solution of 7. So x is equal to 1 into solution. So we take x is equal to 2. Then we find x2 is equal to a plus x1 plus 7a1. Okay, x2, what is x2 is equal to x1 plus the number we found a1. So that is 2 plus 7 times a1. Next we substitute it back in this equation to get 2 plus 7a1 the whole cube plus 3 into 7 a1 the whole square minus 2 into 2 plus 7a1 plus 5 congruent to 0 mod 7 square. And now when we expand this, simplify, and we get 3 plus a1, which is congruent to 0 mod 7. And now we have to think what value of a1 would make this true. So when we give a1 equal to 4, we get 4 plus 3 to 7, which is congruent to 0 mod 7. And thus we can give a1 is equal to 4 is the solution. So we substituted back in x2, 2 plus 7a1 is 2 plus 7 into 4, which is 30 is one solution, congruence modulo 7 square. Next solution is x2 plus x3 equal to x2 plus 7 square a2. Again doing similarly, we find 4 as a solution and substituting it in this equation to get 226 as a solution. Now when we try to f of x modulo 7, we had another solution 1. We tried to lift it with x1. So here when you try, you will get 1 plus 7a1 congruent to 0 mod 7. So here there is no value of a1 that would satisfy this congruence. So we say that 1 is not possible.